Okay, so this video is dealing with what we're going to call alternating series. They're a pretty common thing. So they're any type of series that is kind of flipping back and forth between negative and positive. Usually it's some series that has like either -1 to the n times something, or -1 to the n minus 1 times something, or -1 to the n plus 1 times something. Any one of these is an example of an alternating series. So we have a thing that's called the alternating series test. It's a test for convergence. So if I have an alternating series, and we're just going to kind of play it off as though it's -1 to the n minus 1 times b to the n. Any one of these it'll work with. We're just using this as our example. So this means that, okay, so the series itself is being labeled as a to the n is this. So this means that b to the n is the absolute value of a to the n, because we're stripping off the alternator. And that's going to be true for all n. Okay, so if this is the here and we meet a couple of conditions. One, b to the n is monotonically decreasing. So the part of the series without the alternating part is decreasing monotonically. This simply means that the next term is always less than or equal to the previous term. That's all that monotonically thing means. It means that not only is it decreasing, but it's decreasing in such a way that the sequence never goes up at any point. Okay, if that's the case, and 2, the limit as the non-oscillating part goes to infinity, as n goes to infinity, the non-oscillating part, the Bn, is 0. If I've got these two things, I'm monotonically increasing and I'm monotonically decreasing and monotonically decreasing to 0, then the series, right? This series, the original a sub n series, is convergent. So, all right, so what does the alternating series test say? First, I have to have an alternating series. Then, once I strip off the alternator, it has to be decreasing monotonically all the time, going down. And it also has to be doing so as it's approaching 0. If it monotonically decreases, approaches 0, then not just the sequence, but the series itself converges. All right, so there's a great example of this that we can use. Okay, so it is really, really clear that the harmonic series itself is divergent. But we can make one simple modification to the harmonic series. Instead of having 1 over n, I'm going to have -1 to the n over n. Okay, this thing is what we call the alternating harmonic series. So this thing is, like, if you think about this series, you get -1 plus a half minus a third plus a fourth minus a fifth, so forth and so on. So it's the harmonic series, but we're changing the sign at each term. All right, so let's apply the alternating series test to this. All right, so b to the n is going to be 1 over n. This is clearly decreasing monotonically. One over n plus 1 is always less than or equal to 1 over n for all n when I count 1, 2, 3, 4, so forth and so on. So this thing is definitely decreasing monotonically, right? Okay, so we've met criteria number 1. Criteria number 2 then is the limit as n approaches infinity of b sub n, which is 1 over n equals 0. We meet that. So we've met criteria number 1, we've met criteria number 2. So according to the alternating series test, we conclude that this sequence converges. We don't know what it converges to. Well, we can figure it out, but it's like some weird number. But it does, in fact, converge, okay? So here's what's going on. On one level, we've got that the harmonic series diverges, but when I put an alternator on it and have it go negative, positive, negative, positive, this guy turns around and converges. So there you have it. We have the idea of an alternating series. We have a test for convergence for alternating series. It's pretty simple. That's it.